So both propan-2-ol and propanone are small 3-carbon molecules. Therefore, because of this small size and permanent dipole nature, they interact with water molecules. Therefore, they are fully miscible. The intermolecular attraction forces involved are with propan-2-ol and water form hydrogen bonds, and permanent dipole interactions between propanone and water molecules. Van der Waals interactions are negligible when it comes to this kind of small sized, small alkyl group containing molecules. Then moving on to boiling temperature, between propan-2-ol molecules there are hydrogen bonds as alcohol groups are there, which are highly polar, and in propanone it is carbon double bond O bonds, which makes the molecule a permanent dipole but not causing hydrogen bonding. Therefore, as expected, the boiling temperature of propan-2-ol is increasing because more energy is required to overcome the intermolecular attractions between propan-2-ol compared to propanone. Therefore, the boiling point is higher in propan-2-ol compared to propanone. Part E, you should assume that there is complete combustion and that all energy produced is transferred to water. Specific heat capacity is given, but most probably this could be a printing mistake in the paper. The specific heat capacity is given in units joules per Kelvin per mole. It should be corrected as joules per Kelvin per gram. And delta H conversion of biopropanol is given, and assuming that biopropanol is 100% propanol, we can start our calculation because we need to know the molar mass value which can represent biopropanol. So for that, I'm going to use the molar mass value of propanol by assuming biopropanol is completely propanol. So that value I'm getting as 60 grams per molecule. I'm dividing the mass of biopropanol burnt, that is 1.02 grams, by 60 grams per mole to get the amount of biopropanol that is burnt, because I know the molar enthalpy of biopropanol. So I should know the amount of biopropanol actually burnt in this experiment. To do that, I can multiply the molar enthalpy by the amount of biopropanol that is burnt. Then I can equate that value to the energy required to increase the temperature of water, as in the question it is allowed to assume that complete combustion happens and all the energy produced is transferred to the water. So in that case, I'm getting mc delta theta for water equals the energy produced during combustion of biopropanol in this experiment. By burning 1.02 grams of biopropanol, whatever the amount of energy is produced is completely used to increase the temperature of water. That is what is our assumption. Then I'm going to apply the values. In that case, I'm finally ending up with the equation T1 minus T2, that is delta T, equals minus, I have converted the joules per mole value, kilojoules per mole value, molar enthalpy value into joules per mole for the convenience. So the units cancel off. And when I simplify this equation, I'm getting the delta T value as minus 41.09. When I simplify that, I'm getting minus T2 equals minus 41.09 minus T1. This is a difference of temperature in kelvins that is equivalent to a difference of temperature in degrees Celsius. So straight away I'm converting that into degrees Celsius. So I'm getting T2 equals 41.09 degrees Celsius plus 20 degrees Celsius, and the final temperature is 61.09 degrees Celsius, the final temperature of water. Biopropanol has a higher octane number than bioethanol. Name the process carried out on alkanes obtained from crude oil to increase the octane number of a fuel. So in your curriculum, you have learned two processes which increases the octane number of a fuel, catalytic reformation and catalytic cracking. If it is a high molecular weight compound, we can use catalytic cracking to increase the octane number. And if it is a simple cyclic molecule or an isomer which is having a poor octane number, to improve that, we can use catalytic reformation. So the answer would be catalytic reformation or catalytic cracking, as the what type of alkanes that we are using, that we have to work with, is not specified.